Welcome to the lecture number 6 of Physics 401A. So in this lecture, we will discuss some application of Lagrange formulation. Okay. So first we start with very familiar example, which is the example of simple pendulum. Now, it is true that in simple pendulum or whatever be the physical problem, sometimes to make our concepts clear, it is useful to draw figures. But Lagrange, when he originally developed this subject, he claimed that in his procedure, we don't have to draw force diagrams. So in order to pay some respect to that, I will somehow not draw any figure for this type of problem. Although, like diagrams are sometimes very much useful even to understand the geometric concept, constraint, and also what is really going on, and to calculate several distances geometrically or trigonometrically. Okay, so I somehow will not use any figure in the applications which I will discuss today, but it is somehow customary, or rather if you find it necessary, do not hesitate to draw a figure. Okay, but you will see that you will not need any force diagram or free body diagram, what you say in general, to solve a problem or to derive the equation of motion of a mechanical system if we use Lagrange's formulation. So for simple pendulum problem, we first have to construct the Lagrangian of the simple pendulum system. Now at first we have to see what is the symmetry and what are the constraints for the system. So the constraint of the system, okay, the system is like that. The string of the pendulum is massless. Okay, let me just underline this part. The string of the pendulum is massless, the string. Okay, yeah, okay. And this has a fixed length L, and at the end of the string, a bob of mass m is attached, which is a point mass, so it doesn't have any finite shape. It is just a point like thing, and this one is moving vertically in a plane, let's say the plane of the paper, for example. And as we can also understand that the only generalized coordinate here is theta, because the length is fixed. So once again, this is a problem with 2D polar coordinates, as I discussed somehow in lecture number 4, and then the only generalized coordinate for the system being theta, we can easily construct the corresponding Lagrangian. Now just one second, here when I am talking about theta, I do not put any constraint on the value of theta. That means theta can be very small, moderate or large, whatever it is. Okay, but it is the angle between the vertical, that means the mean position of rest, and the current or instantaneous deflected position. That's all. For the Lagrangian, we know for a usual mechanical system under conservative force field, it will be T minus V. Now V is for this case, V is the gravitational potential energy. So the kinetic energy will simply have half m L theta dot square. Why is this for? Because in plane polar coordinate, the velocity has two components. So along r cap it has r dot component, and along theta cap it has r theta dot component. So here r dot is 0 because the length is fixed. So r theta dot component will be the only surviving one, and r is also a constant, so it will simply be L theta dot. Okay. So T is equal to half ml square theta dot square, and the potential energy is V, which is equal to mg L minus L cos theta. Now here in our case, we have assumed that the mean position of rest, which is the minimum possible position of the bob, is considered to be the reference potential level. That means at that point the gravitational potential is assumed to be 0. Then you can easily understand that when this bob is making an angle theta with the vertical, then the vertical distance from the mean position of rest to its initial, instantaneous position is nothing but L minus L cos theta. Okay, you can simply think of the figure which you have, which you have drawn many times before, or you can also draw a figure to cross check. So, Lagrangian is half ml square theta dot square minus mg L minus L cos theta. So, you see that here the system is consisting of theta, both theta and theta dot. Okay. So this is a one-dimensional problem because we have only one couple of generalized coordinate and generalized velocity. So the corresponding Euler-Lagrange equation will also be only one in number, and that will be d dt of del L del theta dot minus del L del theta, which is equal to 0. So if we now do this d dt of m L square theta dot, so m L square theta dot is nothing but del L del theta dot. If you do that, so when you do del L del theta dot, theta is constant once again, so it will simply act on this term, so it will be m L square theta dot. That's exactly what I have written over here, and you have minus del L del theta, so this term will then be unaffected, and this mgl is a constant, so it will be plus mgl cos theta, so del theta of that is minus mgl sin theta. So here exactly what I have written. Okay. Now by further simplification you can say, so theta double dot, which is d dt of theta double dot plus g by L sin theta is equal to 0. So that is the equation of motion for a general angle theta, for any arbitrary angle theta of the pendulum. Okay. Now for a very small theta, sin theta is proportional to, or rather is tending to theta. So we have this simplified equation, theta double dot plus g by L theta is equal to 0. Now remember this one, just solving this form, generally for an arbitrary theta is not possible, or rather not evident analytically. Whereas if you do this assumption, then you have a very easy and simple form which you can directly do analytically, and you know that the solutions will be sines and cosine type of trigonometric solution in the, as a function of t. Right? So theta will be, let's say, some a sine theta, a sine omega t plus b cos omega t, where this omega will be root over g by L, which is the frequency, angular frequency of the pendulum. Okay, that you all know. Now remember, notice one very interesting fact. In this total problem, you have derived the equation of motion, but unlike your previous experience, you have not considered the tension of the string. Beforehand, you had to balance the forces, the component of the, component of this gravity, and which is balancing the tension of the string. So this type of thing were there, but here you don't have to do anything. You even don't have to mention that the string has a tension or something. Just you have to know that which external force is working on that. Okay, so because the tension force here is the force of constraint, so as I said, just if you can remember, the force of constraint is not needed to be mentioned here. Okay, on the other hand, the external force which creates here a global potential field, that is important. Now that simplifies the problem approaches very much, because sometimes we are also confused that whether tension is doing this one, which one is balanced by tension. So for simple pendulum, the case is very simple, of course, but if it is a bit complicated case, and then sometimes we also think that, okay, friction will be over there, friction. So friction is another type of force of constraint sometimes. You will see, maybe we can discuss some problem later. Okay, now I am going to another type of pendulum, that is called spherical pendulum. Okay, how many of you have seen spherical pendulum? I don't know, but sometimes you can see in the children's toy shop, you can have this type of thing. So a bob is basically, bound in at a point, and this one is, so the bob is describing, or rather navigating on the surface of an imaginary sphere of fixed radius r. So as again the constant is that the bob should move on the surface of a sphere of fixed radius r. So the pendulum now has 2 degrees of freedom, theta and phi. And as we all know, again the component of velocity in 3D spherical coordinate is r dot r cap plus r theta dot theta cap and r sine theta phi cap, r sine theta phi dot phi cap. Then basically you can finally say that as r dot is equal to 0, then the total kinetic energy is nothing but half mr square theta dot square plus sine square theta phi dot square. Okay. And again, if we also say that the spherical pendulum's equatorial plane, that means the equatorial plane of the imaginary sphere is considered to be the reference potential reference level of the reference potential level, or the reference level of the potential, the same language actually. Then at some angle theta, which is it's making with the so basically just a minute. So if its vertical distance from this equatorial plane is mgz, then that z will simply be r cos theta, where theta is the co-latitude. Okay. So you all know that phi is known as the azimuth-along angle and theta is the co-latitude. So co-latitude simply means that this is the complementary angle of the latitude. Okay. Again, here I am not drawing a picture, but if you find it useful, please do not hesitate to draw a picture for your convenience. Now the Lagrangian is L is equal to T minus V, and which I have written here. And now we calculate what this dl. So as we can see here, so this is a 2D problem. So we have two couple of generalized coordinate and velocities. One is theta theta dot, another is phi phi dot. But just have a look on this Lagrangian's expression. You have theta dot, phi dot and theta. You don't have phi explicitly. So in this Lagrange's expression, you have two type of generalized velocities, but only one type of generalized coordinate. So the generalized coordinate which is absent in a Lagrange's expression, although this is a varying quantity, this is not fixed, although this is a varying quantity, but it does not appear explicitly in the Lagrange's expression, is known as a cyclic coordinate. I will talk about it or discuss about it later. Okay, and that will have some interesting property. Okay, so here you can see that we will have two Euler-Lagrange equations corresponding to theta and phi respectively. So for theta we have d dt del L del theta dot minus del L del theta is equal to 0, and for phi we have d dt del L del phi dot minus del L del phi is equal to 0. We can also calculate now this coefficients del L del theta dot. If you do so, phi dot and theta will be kept constant, so your del L del theta dot will simply be m r square theta dot, and del L del theta, if you do from here, you can see that you have two contributions. One from this contribution, so it will be del L del theta, it will be half m r square phi dot square times 2 sine theta cos theta. So finally it will give you m r square sine theta cos theta phi dot square, and that will be minus mgr minus sine theta, that will be plus mgr sine theta. Okay. Again you also have del L del phi dot is equal to, so then theta dot and theta are kept constant, so you have contribution only from this term, which is half m r square sine square theta times 2 phi dot. Okay, and 2 cancels out, and so you have m r square sine square theta dot. Okay, and finally you have del L del phi is equal to 0. That's exactly what I just said. Okay. Now you see that if you have this type of cyclic coordinate, then this part is 0. So you can easily say that ddt of del L del q dot is 0. So del L del phi dot, okay, is a constant of motion. Now remember I said that t the kinetic energy del T del Q dot is called the conjugate or generalized moment, generalized momentum, okay, corresponding to the generalized coordinate Q. Now here you can see that if your potential function is independent of phi dot, then del T del phi dot is equal to del L del phi dot. So I can say also in this case del L del phi dot is the generalized momentum corresponding to phi. So for this type of case where your potential function is independent of the generalized velocities, you can always write that for a cyclic coordinate, your corresponding generalized momentum will be conserved. That's exactly you can see here. Now, as this is conserved, this one is conserved, you can write sine square theta phi dot is equal to constant by mr square, which is equal to k by mr square. Okay, I call this as h, k by mr square as h. Okay. Now, if you just write this equation, so this Euler-Lagrange equation for theta should be looking like this: theta double dot minus sine theta cos theta phi dot square minus g by r sine theta is equal to 0. If you just replace all these values in this equation, okay, and from this equation you just have the information of one constant of motion. That's very important as well, and you can. So in this equation, theta double dot minus sine theta cos theta phi dot square can be substituted in terms of theta, and that will be k square by m square r to the 4 by sine to the 4 theta minus g by r sine theta. Okay, so that is the whole total equation, and finally you have, so sine theta will cancel out, and cos theta will be, so cos theta by sine theta is cot theta, and 1 by sine square theta is cosec square theta. So that is exactly the, yes, that is exactly this term, and k square by m square r to the 4 is h square, and that is minus g by r sine theta. Now that is the, this is the equation of motion of a spherical pendulum. Okay. Now maybe you can think, so whether you can really discover or rather recover the equation of a simple pendulum from this equation. Okay, and also think that in spherical pendulum you have a minus sign. So if you, even if you just forget this term, you will have theta double dot minus g by r sine theta, whereas for simple pendulum you had theta double dot plus something theta. Okay, so can you reconcile those two, or can, I mean, are they different things? The question is that whether they can, one can be, I mean, the simple pendulum equation can be recovered from that. If yes, why? If not, why? Okay, think on that. So here I end this part of the lecture. Okay, thank you very much.